Hi there. In this video, we're going to be seeing the formula for the secant line and the tangent line at a just random point, x equals a, and see some applications, simple applications of that. This is section 2.1. It's also sort of foreshadowing chapter 2, where we're going to be doing these more in general. All right, so to find the general formula, I'm not going to start with a specific function. I'm just going to start with some random function. So I've graphed just something squiggly. There's a random function. We don't really need to know the equation because we're doing it for any equation. And we need to find the slope of the secant line and the tangent line at a particular place. And we're going to label that place x equals a. So on the x-axis over here, we're going to have some value a, which will have a y value of f of a. Remember, you plug a into the function and you get the y value. So here's my y-axis with the point a comma f of a. Now, to find the slope, whether it's a secant line or a tangent line, you need 2 points. Secant line will be any 2 points. Tangent line wants those 2 points to be very, very close to each other. Now, I can't really, with the resolution of these cameras and pens and stuff, I can't show you 2 points that are extremely close to each other because it just kind of blurs in. So I'm going to be using 2 points which look kind of far apart, and we're going to imagine that they're getting closer and closer and closer together. So that's our second point over here. Now we could call this B, A and B makes sense. We could call it different kinds of things. And you look on the internet, they will call the second point different things. It's very traditional, and the author of your textbook does this as well, to call this A plus H, which seems a little bit odd at first. But basically, I say I'm starting at the A value and I'm adding in a little bit more. So there's A, and I'm adding in just a smidgen, just an H amount. We really want H to be very close to zero. That's our big goal, right? If it's very close to zero, then we can get a good approximation for the instantaneous rate of change, which is the tangent line slope. So that's what we really want, but we're going to show them separately. And just remember that H is how much further you've gone, and we really want H to be close to zero to get a good approximation of the instantaneous rate of change. Well, if A plus H is our new X value, then our corresponding Y value is when you plug in A plus H into the function, and we call that very dramatically F of A plus H. So there's my y2, y1, x2, x1. So if I'm going to be calculating the slope of the secant line, so this is secant line. Come on, pen. Hold on a second. Okay, so a little technical error there. So secant line slope, we'd have to do our change in y's over our change in x's. The y values, well, we have the second y value in red, which is f of a plus h. And then we have that other y value, the lower y value, which is f of a. And the corresponding x values would be a plus h and a. So that's the y2 minus y1 over x2 minus x1. Well, the top doesn't really simplify because we don't have a specific function. We don't know how to plug stuff in. We don't know how things will simplify or anything like that. But the bottom can be simplified because we have a plus h minus a. This a right here and this a right here subtract to be zero. So we can simplify this formula. The slope of the secant line slope, is f of a plus h. That's our y2 value minus the FA number And the bottom is just going to be written as h, because those a's will add to 0 or subtract to 0, I guess. So that's the formula for the secant line. That's the formula we're going to be using quite often. But remember, we really want h to be close to 0, because when h is very close to 0, we can estimate or even calculate the tangent line, which is going to be the instantaneous rate of change. So the tangent line slope, tangent line slope, is going to be the same thing, except we want those 2 points to be very, very close together. And remember, h is how far apart they are. H is how much you've moved beyond A, and we really want h to be very, very close to 0. So the way we write h to be close to 0 is we use this symbol here, LIM, which stands for limit h approaches 0. Next video, I'll show you how to calculate these limits. We kind of did that already when we did our calculations, our estimates of instantaneous rate of change in the previous video, if you want to go check that out. But we're going to write the limit, or the idea that h is very, very close to 0 of our secant, right? Remember, it's just the same slope equation, so nothing's really changing, except that in order to get a tangent line, in order to get an instantaneous rate of change, you're going to have to make the 2 points extremely close to each other, which is the idea of this limit when h is very, very close to 0. H is how far they are apart. So if h is 0, then these 2 lines, or these 2 points, get basically right next to each other. Well, I forgot the bottom part here. So that's your formula for the tangent line slope. Right. To find the tangent line at a particular point, well, to find the equation of any line, you need the slope and you need a point. Now we're at x equals a. So the point is going to be a comma fa. And the slope, well, we're going to calculate that using our formula here, right? y2 minus y1 over x2 minus x1, or fa plus h minus fa over h, when h is very, very close to 0. And then we're going to use our sort of formula that we normally use, which is y minus y1 equals mx minus x1. That's just say x1. And you just fill in the y value, which is fa. And the x value, which is a. And once again, it's traditional to move this fa to the other side, to make it y equals. So I would do that by adding fa to both sides. Fa. So let me get rid of it here and just shore this up. So that's my equation of the tangent line, right? We needed a point and a slope, and we put it into our point slope formula. All right, let's see an example of that. So I have this function here, y equals x squared, very simple function. And we're going to find the equation of the tangent line at the point where x equals 3 and the point where x equals a. Now, to find the equation of the tangent line, we're going to have to find the equation of the secant line, the slope of the secant line, and make those 2 points really, really close to each other. Well, we know what that formula is. The formula is f of x plus h minus f of x over h. And we need these things, we need h to be really, really close to 0. So let me make a little bit more space here. And I'll write the slope is equal to this fraction when h is really, really small. Okay, so we know what x is. It's not a random place, it's actually 3. So this is going to be equal to, oops, that should say h is getting close to 0, not x. And then we plug in 3. So we get f of 3 plus h minus f of 3 over h. All right, well, still looks kind of messy, doesn't it? But we know the actual equation. The equation is y equals x squared. So if x was 4, you plug in 4, you get y equals 4 squared. Well, we know the x value here is 3 plus h, and we know the x value here is 3. These are x values. So we're going to plug those into the equation. So if I plug in 3 plus h, I get 3 plus h squared. And if I plug in 3, I get 3 squared. So that's f of 3 plus h minus f of 3. And all that is divided by h. And I did forget my little limit thing here. Math folks will get mad at you if you forget to write the limit thing there, because it's supposed to be very precise and stuff like that. Until you do the limit, you're supposed to write the limit. Like until you do the square root, you're supposed to write the square root symbol. Okay, anyway. So let's do a little algebra. 3 plus h squared is 3 plus h times 3 plus h. If you want to write it out and use like the FOIL method or whatever method you use to multiply out binomials, go ahead and do that. It ends up being 9 plus 6h plus h squared. Remember, you have to multiply it out. That's where the 6h comes from. 3 squared is 9. Get an h on the bottom. Yes, I forgot my limit again. I'm only human. Okay, so limit h goes to 0. Okay, we're almost done. We're almost done. All right, notice that on the top, you have a 9 and a minus 9, and those add to 0. So we get 6h plus h squared over h. And we can do some simplifying. Some people like to factor to simplify. I tend to just do the division. So 6h over h plus h squared over h. Right? Each one is being divided by h, so I divide each by h. And that gives the limit as h goes to 0. 6h divided by h, the h's divide equal 1, so this is 6. H squared divided by h, the h is simplified to be h. Well, that may be not satisfactory at this point, but remember, the idea here is we want h to be very, very close to 0, like 0.00001 or something, right? We want h to be really, really close to 0. So what is 6 plus something which is really, really close to 0? 0.000000001. Well, it's 6.000000001, right? And we're just adding that on to 6. If we want h to be so close to 0 that we're going to get an extremely good estimate for this instantaneous rate of change, then this becomes 6. H becomes effectively 0, and so 6 plus something which is effectively 0 becomes 6. So we have an approximate instantaneous rate of change of 6. All right, so now we know the slope. Slope is equal to 6. To find the equation of a tangent line, or any line for that matter, you need a slope and a point. But we do know a point. We know when x equals 3, y equals 9. How do I know that? Well, remember, we're looking at x equals 3. That's our objective. And we know that y is equal to x squared. So in this case, y is equal to 3 squared, and therefore y is equal to 9. So then I just write out my equation. Y minus y1 equals m times x minus x1. Move the 9 over there because I have good math manners. And that is the equation of the tangent line for the function y equals x squared at the point where x equals 3. My last example, my last point here is that everything we did with the number 3, we could do with any number. We could do it with 5 or 10 or 2.7 or whatever number you dream up. So we could just do it with the letter A. And nothing really changes. All our calculations are going to be the same, except that everywhere we put a 3, we're going to put an A. Right? So we have the slope. We had f of 3 plus h. So we're not using the 3, we're just using a. So f of a plus h. Oops, got to leave space for our limit. Don't forget that, Jim. Limit Okay, f of 3 plus h becomes f of a plus h. F of 3, remember we're not doing it at 3, we're doing it at a, so minus f of a over h. I mean, that's exactly the formula, right? That's the formula that we discovered up here because it said at the point x equals a. So that's the same formula. So yes, of course, it's the same thing right there. Let me put me up there. Okay, so that's our general formula. We do actually have an equation specified in this time. So we're not doing a random equation. We are doing the equation y equals x squared. So we can calculate this. We would plug in the x value. The x value is a plus h. So when I plug it into our actual equation, this is our equation, you get that value squared. And then you plug in a into that equation and divide by h. And that is exactly the same as this step right up here. Instead of 3 plus h squared minus 3 squared, we have a plus h squared minus a squared. And we're going to continue the same calculations. We're going to square things out using our algebra. If I square a plus h squared, I get a squared plus 2ah plus h squared. I'm going to subtract a squared, divide by h. That's this step right here. Square things out. I noticed that I have things that combine together. People like to say cancel. I'm not a person who likes that vocabulary very much. This a squared and this minus a squared combine to be 0. So we don't have to write them. They cancel if you like to say it that way. So we get 2ah plus h squared over h. We can simplify these using a factoring or just by dividing. Hopefully this is sounding familiar. Right, we just divide them, right? That's what we did over here. Just divide them. And then we're going to simplify. 2ah divided by h. The h is divided equal 1. So I'm left with 2a. H squared divided by h simplifies to be h. And remember, we want h to be as close to 0 as possible. So this is going to be 2a plus some very, 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 very small number, like 0.00001. Remember our argument that if that number is so tiny that it doesn't make any effective change to the original number, 2a in this case, then it just becomes 2a. So that's our slope. Our slope is that number 2a. Now, it doesn't have an actual number, but remember, we didn't do it at x equals 3. We did it at x equals a. So I didn't give you a number for x. So you shouldn't really expect a number at the end. You should expect something in terms of a, which is what I gave you. So our slope is equal to 2a. What's our point? Well, we know our point because we know the x value is a, and we can plug that into the equation and get a squared for y. If you're not sure how I got a squared, remember the equation that we were given was y equals x squared, or I guess f of x equals x squared was what it said specifically. But nonetheless, our function is x squared. You plug in a value for x, and the y value is x squared. So I plug in a, I get a squared. And then my equation of a line is y minus y1 m x minus x1. I just plug in the things. The y value here is a squared. The m value is 2a. And the x value is a. Be nice and put the a squared on the other side. And that is your generic equation of the tangent line at the point x equals a for the function f of x equals x squared. All right, so my next video, I'll show you how to calculate limits in different ways. But hopefully now you understand what this big idea here is behind a tangent line slope, secant line slope. Please reach out if you have any questions or need help with anything. All right, well, I hope you have an enjoyable day.